Okay, so what I'll talk about now is graph theory, and the idea of what we're doing kind of on the blackboard here. We're going to eventually, in maybe other computer science classes, will implement software that can go through graphs. But a graph is basically a collection of points. So I'll just put some points up on the board, label them A, B, C, and D. So these points are vertices, and some of them may be connected to each other, and some of them may not. And if they are connected, we'll draw an edge between the two to say point A and point B are connected to each other, and point B and point C are connected to each other, and then maybe point B and D are connected to each other. And in other different computer science classes, you might have to write software that can capture this. And that might be done in computer science. You might have an array. You could have a two-dimensional array that goes A, B, C, and D, A, B, C, and D. And they could have 0, 1, or true or false values, and you can make them true if they're connected and false if they're not. So if A is connected to B, we'll put a 1 in it. If B is connected to A, D, and C, that means B is connected to A, D, and C, and C is only connected to B, and D is connected to B, and actually this should be symmetrical. D is connected to D, yeah, and everything else would be a 0.
Okay.
So this is one way, and then in your other computer science classes, you might find there might be a more efficient way that if you then started to run computer programs that say, let's say these points end up being cities like New York and Los Angeles and then London, so maybe, and these connections mean can you drive there? So New York and London would not be connected, but New York and Los Angeles would be. And then you can answer questions based on this map, can I drive from this point to that point? And you'd have software that would answer yes or no. Well, it would end up going through this data and then eventually figuring out a yes or a no. So that's one way. I just wanted to bring up one way that we could represent a graph in computer memory. But there are some more efficient ways to do that. But for now, we're going to just, this is just like blackboard related stuff. So we'll say a graph, we represent this with the letter G, is equal to a combination of vertices and edges. So you see that, that's kind of like a high level definition of what a graph is. So this whole thing is G. The vertices are A, B, C, and D. And the edges are really, if you want to draw the edge set would be A to B. Sometimes it's even drawn like there's a connection between A and B.
B to C and
B to C and B to D. So we have a collection of vertices, a collection of edges, which obviously have to connect existing vertices. Put it all together, we call that a graph. Okay. So now a path in a graph if our graph has a way of getting from one point to another, so if we had a graph like A, let's say we had a graph like this. There's no particular order to these letters, they could be names. You could have big names, but as long as there's 26 or less points, we could just use one letter. Okay, so now let's say we had a question. It seems to be a path from everywhere to everywhere, but is there a path from point A to point F? So that would be, can you go from, it doesn't have to go directly from A to F, but can you get to something which gets to something which gets to something which eventually gets to F? Yeah. And so this will be like, in computer science, you'll be given a graph, you'll be answering questions like, can I get from A to B? And it'll be a yes or no question. And then maybe you can, and you want to find what's the fastest way to get from A to B. So like GPS systems are basically a bunch of points and graphs and what routes that connect them together, and you want to find the best one. So those are the type of questions we want to go with. So this is just kind of a high level, just the ideas of graph theory. So now the question is there a path from A to F? And actually, there's a path from every point to every point here. And then another interesting question is, what's the length of the path? So if we took the path that goes A to B to D to E, back to C to F, this path has length. So the length of a path is how many edges? 1, 2,
5.
3, 4, 5. So this would have length 5. There's also a path that goes A,
B,
B, C, F, and that has length 4.
3.
3. Okay. And that looks like the quickest
Shortest
path.
path.
Right, if our goal was to find the shortest one. So now there's the idea of, do graphs have finite paths in them, or is it possible they could have an infinite size path? So an infinite path what would have to happen? So does this graph have an infinite path from A to F? Can we come up with a path that actually has infinitely many edges? So, and you're allowed to reuse an edge that you've used before. So as you're traveling over the path, you can reuse an edge. So what we can actually do is we could go from A
To B.
to B to, let's say, C, E, D.
And again to B.
Right, and then just keep, so these 4 steps, we could kind of note it that way.
Right.
And sometimes they'll put a star here, meaning you could do this as many times as you want. And if we did this infinitely many times, there is an infinitely long path that goes from A to F. In order for there to be an infinitely long path from A to F, the graph would have to have somewhere in it, at least once, or the path would have to have somewhere in it, what we're going to call a cycle. And a cycle is by definition a finite path at which the initial vertex and the coincidence vertex or the terminal vertex are the same one. So if we have a path like B, C, E, and D, sorry, B, C, E, D, back to B, this path, which is of length 4, 1, 2, 3, 4. This is a path of length 4. Since the initial node and the last node are the same, they're a cycle. So that means we can travel it over and over again. Okay, so then the definition of a simple path. A simple path is, so what do you think a simple path would be? That would be a path that doesn't use the same vertex more than once.
Okay.
The same edge more than once. Okay, so what would be a good way to symbolize the edge, like the edge between B and C? Should we come up with, like one thing we could do, we could start labeling the edges with Greek letters maybe, but if we just use the 2 points at each end and then maybe draw a bar over it, that's a pretty common way to refer to it. So we could say B, C with a bar over it. That means the edge from B to C. Now notice in this there is no idea of first and last. Like it's, if there's an edge from B to C, there must be an edge from C to B. There's no direction here. It's just either they're connected or they're not.
Okay.
So a simple path would not use the same edge twice. So an edge, so basically, and to use the same edge twice, you'd have to somehow get to a point, take a path somewhere, and then come back to that point and continue. So the It doesn't mean you followed a cycle more than once, but you could have done this. Like, we could have had a graph like this. A goes to B. B goes here to here, back to B, and then maybe off to F. So we could actually go from A to B to C to D, back to B to E and to F. We visited this vertex 2 times,
Right.
but we've never traveled the same edge twice. So that path, this would still be considered a simple path, because we haven't used the same edge twice. Is there a simple path in this graph? Well, the A, B, C, F is a simple path.
Right.
And the A, B,
D,
D
E, C, F is also
is a simple path. But once we start going this way, we're gonna have to reuse this edge, and then we would not have a simple path. Okay. So they wanna have a name for a path that never uses the same edge twice. And then we need a name for one that does use at least one edge twice, meaning a path that's not simple. And they call that a composite path. Means not simple. Not a simple path. That means at least one edge was used at least more than once. Okay. And then, so then we have the length of the path. Okay, and then just to have a name for a path where the same vertex was used twice. Even though we didn't use the same edge twice, this vertex was used twice. So for the path, A, B, C, D, B, E, F. For that path, every edge we used in the path is a unique one. We never used it twice. A, B, B, C, C, D. We never used the same edge twice. However, we did use the same vertex twice. So this would be a path that does not use the same vertex twice is called an elementary path. That's too bad, simple path and elementary path. Elementary usually means simple or very beginner,
Right.
but it's, you can't really, I wouldn't expect anyone to remember this, but one of them means you don't use the same edge twice, and one of them means you don't use the same vertex twice. It would have been nice if it had a name like simple path V and simple path E.
Yeah.
Then we, but anyway, this is an elementary path, does not use same vertex, does not use the same vertex, again. And in the notes I have a more formal definition of it, but, so we don't use the same vertex twice, and that's called a simple, an elementary path. Okay, so the graphs we've talked about so far are what are going to be now called, because we're going to add a new concept. The concept we're going to add is we may, for the edges, we may have an arrow on them. So let's say there's an arrow going from B to C. That would mean you can get from B to C, but you cannot necessarily get from C to B. So this wouldn't apply to like roads on a map. What would this apply to? I'm trying to think of a simple example where you can get from one thing to another, but you can't come back. So it's kind of like a one-way door where you have a pass to get into a room, but once you're in the room, you can't get out. Something along those lines. But there'll be real-world examples of this. So the types of graphs.
How about a queue, sir?
A what?
A queue. You can get in through one Q.
Okay, well, to Q, that's a line to get into something?
Yeah, once we enter, we have to go out in the same direction, but we cannot like come back.
Okay, yeah.
Q
basic-
data structure.
Oh yeah, a Q data structure, right. So really, a Q data structure is the implementation of the next type of graph. But I'm just trying to think of a real world example, like maybe, if you get, at a supermarket, you get online to one of the cashiers, assuming you can't get off the line and shop again. Once you get online, now you can't go back to the point you were at before. So if we had a graph where, so there's a new thing we're going to add, the ability, and this is kind of optional. We could have A, B, I'll stick with the same format before. C, D, E, and F. But now I'm going to put orientations on the graphs. So the graphs we've talked about so far, we're now going to have to give those a name. We'll call those undirected graphs. They have no direction, the edges. And now these ones we'll call directed graphs. So this will be a directed graph. And a lot of times they're referred to as digraphs. So if it went like this, so now the edges have a direction to them. And if that's the case, now it's the same graph we had before, but now the question is there a path, let's say again, from A to F? In this case, it turns out that there is. Oh yeah, just one thing. So now if we wanted to represent this in computer memory, we could, and here's where this matrix might make sense.
Right.
Because now for every entry, like let's say we're considering the arrow goes from here to here.
Okay.
We would represent this graph in a two-dimensional array by saying A connects to B, B connects to D, D connects to E, E connects to C, and C connects to F. C connects to F. 1, 2, 3, 4, 5 edges. 1, 2, 3.
And B connects to C. We haven't like included an arrow there.
Oh, yeah, I should have given an arrow. Let's do this.
Okay. C to
So,
B will be 1.
C to B. So C connects to B. C connects to B. And everything else would be a 0.
Right.
What's this? B connects
To D.
What is this one?
E connects to C.
E
So
connects to C, that would be this one. Okay. And F connects to nothing. Okay. And actually, we could almost argue, do nodes connect to themselves? Does B connect to B? Technically, you're there already, so we could, so the diagonal is the ones where they connect to themselves. We could go like this. Okay, so this computer memory represents this picture. And now we ask ourselves the question, can I get from A to F? Like a yes or no question, can I get there?
yes.
And the answer, yeah, so we would have to, this would be the input to your computer program. You would then figure something out and eventually you would say yes. So, and that's what we kind of want to get into, like just how do we go from graph theory to computer solving problems? So, what would end up being the answer? The path would go A to B to D to E to C to F. That path works. Now another question, does this graph a completely different question, but comes up a lot in computer science. Does this graph have a cycle in it? Can you get from any point in the middle, start at that point, and then go somewhere and come back to that point? Is that possible? And that cycle path, so this is the path from A to F. And they usually lose that little squiggly line. That means a path starting here and ending there. Is there a cycle in the graph? So can we start at some point and then go around to another and get back to that point?
B, D, E, C.
B to D to E to
C to B.
Back to B. So this is a cycle. And sometimes even draw underneath at the first point, or it's implied. If you see the first point and the last point are the same, you know it's a cycle. Okay. So, you can kind of see some graphs may have a cycle, some may not. There could be multiple cycles in a graph, right? We could have FG. So now we have this cycle and this cycle, right? So we have the one you just pointed out, which goes like this, and then we have another one here. And, you know what, if I made it like this, we actually have 3 cycles, right? We have this inner one that we had before.
Right.
We have this new one. Well, oh, I'm sorry, this should go this way now. And now I've made another one, which goes like this. It started B, go to D, then to G, then to E, and to C.
Yes.
So there's another one that goes like this.
Oh, that's actually anti-clockwise.
Yeah, this one's wrong, right?
Yeah.
Okay. This one goes this way. Okay. And then we have this one.
And between D, E and G, D is connected to G, G is connected to E, and from E to
right.
D, it's the...
Right.
We don't have
So
a-
did I have it right before then? That's a good one. Let me just clean this up.
Right.
Maybe I had it right the first time. So if
You
we
could
go,
have it from E to G and G to D.
yeah. So we want it to go this way. Oh. Okay.
Yeah.
This one's going this way.
But that, again, it doesn't work.
Oh, okay. Let me do this then.
I did all but 3 the whole part of 5.
Going this way.
We
Then-
could have just 2 cycles, I guess.
No, wait, why couldn't we go this way? Why wouldn't this work?
Yes, sir, that the bigger one
Oh, right, but this
works,
one
but
isn't.
the internal
Yeah,
D,
yeah,
G
okay.
doesn't work.
Well, it would work if it was a non-directed graph. So if we're going this way, and we want to add get to here, from here to here. Okay, this might, yeah, maybe this is a little, this might not be a good one to do a directed. I wanted to do 2 cycles. Well, okay, obviously one other way we could do it is like this.
Or maybe some point in between. between D and E.
Yeah, but that's
Oh,
what I'm doing.
it doesn't work on any of the
Goes this
sides.
way. Well, let's say we went back to the way we had it. So there's a G point, and then we decided to add another arc like this. Looks like a little cheating, but now the connection between D and E, and there's also a connection between E and D. Now, if that's the case, we have the new cycle we added, the one we had before, and now a new outer one, which goes B, D, the outer one would go, make the outer one go this way. So the new one goes like this, over this new edge, and then the outer one could also go like this.
Yeah.
Okay, so with the two-way edge, we now have three cycles in this graph. Okay, so anyway, the graphs can have more than one cycle in them. Could have one, could have many. Actually, I guess, no, not infinitely many, because we have a finite number of points. But, so we might want to run computer algorithms that say, given a graph, how many cycles are in the graph. Is it possible for a graph to have no cycles?
Yes.
Okay, so start over with, obviously in directed and undirected graphs, we can have no cycles. We can have like this, in an undirected graph, that's a graph with no cycles. So really, first of all, the only connection between directed graphs and undirected graphs, basically in an undirected graph, if there's an edge between 2 points, what's the corresponding version of a directed graph? That's, you have the 2 points with 2 arrows. So in an undirected graph means you can go in either direction. So the directed graph equivalent of it would be like this. And everywhere you see an edge, replace it with those two, and now you have a directed graph. So any question you have, if you write a computer software program that takes a directed graph as input, no, I'm sorry, yeah, it takes a directed graph as input and can answer any question. If you wanted to feed it an undirected graph, you can. You just have to convert every edge into these 2 arrows and then go and solve your problem. So it's kind of popular to solve computer questions using a directed graph, because if you come up with a solution, you can always convert the input of this to that and then use the thing you solved, rather than solve the problem twice. Okay, so it is possible for a graph to not have a cycle in it, which makes sense. Right? Oh, well, the one I just drew wouldn't have a cycle in it. And the same could be true for a directed graph. We could have this. Right, so A, B, C, D, E. But there's no cycle, because we can't go around this loop. Everything seems to sink into E and can't get anywhere. So it's possible for a graph to not have a cycle. So if a graph, if G equals VE, that's a graph, has no cycles, then G is a tree. So a tree is a graph that has no cycles.
Okay.
Okay? And so now another interesting definition is components. So if a group of vertices and edges are connected, they're considered a component. We could have a graph that looks like this. A, B, C, D, E, F, G, H. This graph now has 2 components to it. two separate pieces, right? There's no law that says they all have to be connected. So this is a graph with two components. This piece has a cycle in it, this one doesn't. So this component is a tree, this component is not a tree. Now, suppose I did this. Now there's no cycle here, right? Now we have two components, and both of them are trees. When your graph has more than one component that are not trees, if all the components are trees, and there's more than one component, they call the graph a forest, right? A collection of trees. It comes up once in a while in the literature. Okay. So the concept of a tree, I don't know if that's the greatest word for it. It might be more of like an upside down bush is what they meant to say, but suppose we had so here's a picture of a tree. This will be an undirected graph. Suppose we had, another thing we could do with our graphs is at each of the vertices we can store a value. Actually, at the vertice or the edge we can store a value. So if we wanted to, we could, I'm going to draw a picture of a tree, and at the vertices, instead of them just being letters like A, B, C, or D, we could store a value at it if we wanted to. So suppose we had a bunch of numbers, like, or let's say letters. Let's say we had C, D, H, Q, S, and T. A bunch of random letters that we want to store somewhere because people are going to come and look for these things later. So for example, you might have a directory of all the employees at a certain company. So you enter the employees' names, and now people call up, hey, can I speak to so-and-so, and they look the person up. Suppose you have a lot of employees. You're going to be doing a lot of lookups. So one thing we can do, if somebody comes looking for employee Q, we can say, is this Q? No. Is this Q? No. Is this Q? No. And just search everybody until we find someone. But what if we stored them in a tree? So a tree is a graph that has no cycles. And at each of the points we stored a value. And we kept them in an order where, so now I'm taking advantage of, this is a special type of graph. It's the tree kind, so there's no cycles. If I go like this, we have a cycle. So there's no cycles. And I store these letters, 1, 2, 3, 4, 5, 7. 3, 4, 5, 6, 7. If I store them in an order where at every node has exactly two, what we're now going to call children nodes, and always the child to the left has a lower value than the parent, and the child to the right always has a bigger value. So these letters would be stored like this. So this one's done, this one's done, this one's done. Q, C, D, H. If I stored them like this, in a graph, each of the vertices have a value on them. If I went looking for person H, I don't have to search all of them until I find H. I look at this one and I say, is the value I'm looking for less than or greater than Q? If it's less than, well, I know it's not over here. These are all greater than Q. So I know to go this way. So I can even make this a directed graph. It's implied that this is a directed graph because we'll never go backwards. We'll never come down here and go, let me check this one again. So this could be a directed graph with values at each vertex. So we go to this one, and is H greater than or less than D?
It's greater.
Greater than, so we go that way. If it was less than, we'd go that way. And now we found it. So it took 2 steps instead of 1, 2, 3, 4, 5 steps. Now, it's a little more painful to set this up, but once you set it up, if this number of employees got very large, this might make sense. This would have a lot of savings to us. So this type of tree, this type of graph is a tree because it has no cycles. And now we have another rule that every vertex has exactly 2 children. So that's like a special kind of tree. So this ends up being called a binary, meaning 2 children each. You can use it to search for things. So search tree. So this would be called a binary search tree. If we wanted to have 3 children, so then you know, when you take the course, I think 512, where they go over analysis of algorithms, they'll go cover the binary search tree. You put stuff in a binary search tree and you find stuff and you realize you can find it much faster than putting it all in an array. Then people start thinking, wow, what if it had 3 children or 4 children? So like a binary search tree is going to get, as it grows, it's going to get wider and wider. If it had more children, if each node had more children, the tree would be wider but not as high, right? If it's 2 children, it's going to go very deep and get somewhat wide. If it had 3 children, it would be wider but not as deep. And really, when we're searching, it's each level we hop to is work for us, and we'd like to make that as less as possible. But then the problem is, when we get to the point where we're saying, let's say we're looking for h, we have to ask ourselves, is h less than or greater than q? And that tells us to go either this way or this way. Now we'd have to, each time we visit a level, we'd have to ask more questions. So each level would have to have 2 values. And we'd have to say, if we're less than both values, go to the first child. If we're between the 2 values, go to the middle child. And if we're greater than both values, go to the third child. So that each visit, there'd be less visits, but there would be more questioning at each visit. And then this kind of proves that the trade-off, depending on the circumstance, determines whether you should go that way. So we'll save that for your algorithms class. Now, suppose we had a graph like this, that, suppose there was a graph like this. This has a cycle in it, right? Yeah, okay. Suppose the red and the blue lines combined was our original graph. We can take any graph as input and find, so this is a graph that has cycles in it. This is not a tree. It's not in any way a binary search tree. It's basically, yeah, it doesn't have any of those properties. But what we could do, this will sound a little strange, we could remove the edges. So the ones that are in blue, if we remove those edges, this would then become a binary tree, even though the original graph was not. So we could, one of the other things you'll do in your algorithms classes is you'll take a non-binary tree graph and figure out a way to create a tree out of it. And that ends up being, you know, there's a couple of computer science related questions like that, like what's the smallest graph that will leave everything still connected. Obviously, if we turn it into a tree, you can get from one point to another point, but we're removing some edges. And what's the minimum amount of edges we'd have to remove to have a situation where it's still connected? So that's somewhat of a popular question to come up, but it actually comes up in the case where, just like now, what we did was we decided to take graphs and assign values to the vertices. We could also assign values to the edges. We could actually do this. Okay, so let's say we had A, B, C, D, and E. the edges, we could put values on them. Up till now, they've kind of had an implied value of 1, right? If we said that the path from A to C, the shortest path was of size 2, we're assuming this edge counts as 1 and this edge counts as 1. But if we started doing this, if we did something like that and started assigning values to the edges, now if I asked you what's the shortest path from A to C, it used to be, the shortest path used to be A to B to C, which was length 2. Now that we've assigned values to the edges, this path now equals 10. 4 plus 6 is 10.
Right.
Is there a better path? A shorter path, even if it takes more edges? You know, like, think of these as miles between the roads that connect these cities together.
A, E, B, D, C.
Right, so A,
E,
E,
B,
B,
D,
D,
C.
C. Even though it took 2 edges and 1, 2, 3, 4 edges, the total path length is now 2 plus 1 is 3, 6, 7. And that ends up being the shortest path. So when we take graphs and we've now seen examples where we can assign values to the vertices. That's helping us with searching, assuming you make a tree out of it. You don't want to search for something and find yourself going through a cycle. You'll be searching all day, right? So with searching, you kind of want to make trees out of your graphs. So you might be given a graph that isn't a tree and you turn it into the most sensible tree you can, and then you can use that for searching. A graph that has, where edges have values and the vertices just have labels, this is common in like maps. The vertices are cities and the numbers are how many miles between each city. Even roads, like when you use GPS, they're actually solving a problem like this. It's a graph theory problem they're solving. They're trying to find you the shortest path from A to C. And if your algorithm, if you were given this as input to a computer program and you were told, find me the shortest path from A to C, hopefully you'd find this. We're doing this with our eyes, right? We're doing this by inspection, coming up with the answer. But we should be, our program should be able to take in any graph, and let's say we had a program called find shortest path. We would take in any graph and we would find the shortest path between 2 points. Okay, so our graphs can have the edges can have arrows on them or not on them. And the vertices, we have the option to store values into those. So, how could we do that? In a computer, not only the edges we can represent with one of those, you know, rectangular zeros and ones. If we wanted to record the values of each of them, how can we record in computer memory a picture like this? What we could do is, we could say A, B, C, D, E, A, B, C, D, E. What we used to do before was we'd put a 1 there if there was an edge. Now we just put whatever the number is. Right, so we could say from A to B there's a 4. From B to C there's a, B to C there's a 6. And what if there's no edge? The temptation is to put a 0 in, but that makes it sound like they're really close.
Right.
We'd actually want to put in like an infinity or some number that is like so high nobody would ever take that path. So it's kind of implied that there is a edge from from E to C, but its length is infinity. Meaning, yeah, it's there, but don't ever use it. It takes too long. So, yeah, so we put in, we have infinities everywhere else, and the computer doesn't have a value called infinity, so whatever their maximum value is, we would store that. And then we'd answer questions like, assuming this data is true, what's the shortest path? Well, nobody would ever take the infinity path. So your answer should then come out okay. So we just want to convince ourselves that we can represent the pictures we've talked about in computer memory. And what was the other one? If we wanted to have values at the vertices, how can we do that? So we need some way to record the edges are connected, and we have to somehow also record the values. We could, since they don't, the value doesn't have any direction to it, it's just a value, like a person's name or a number. We could make a separate piece of storage, an array, A, B, C, D, E, and just put whatever the value is. S, A, G, Z, T. It could be words, it could be values, whatever that is. And so we can capture the picture in computer memory, in your other other classes, not this particular one, but then you'll take this as input and answer questions like what's the shortest path from A to B. But we just want to cover these definitions. So what you end up doing then is you end up solving the problem by looking at a picture like this. This is how we'll think out the solution. Then once we got the solution, we have to figure out how to program that in. So we just want to talk about we're using the graph theory and these pictures to solve problems, and then we'll worry about coding it up another time.